Hello Math 322 students. In this video we're going to introduce our discussion of circles in Euclidean geometry. You'll remember we've been talking about circles for most of the semester. We will be consulting the text of data for this next part, and you should keep in mind though that we will be using many of the same definitions from before and also the axioms of continuity previously discussed. So you'll remember in particular that back in chapter 3 we discussed the circle-circle continuity principle, the line-circle continuity principle, and the segment-circle continuity principle. And you should assume that these are all true. We're assuming that these hold in the geometry we'll be working with. You should also assume that we'll be working with Euclidean geometry, so where necessary we will assume any parallel postulate we need to hold. Alright, so to go back to our basic definition, earlier in the semester we defined a circle with center O and radius OA to be a set of all points P such that OP was congruent to OA. So in other words, if the center is O and A is a point on there, we'll take the center to be all the points such that the segment from O to P was congruent to the original segment from O to A. Now data's text has an equivalent definition. Equivalently, the circle omega is defined to be the set of all points located at a fixed distance r from a point. Now we called OA the radius. It was a segment before. We can also call this real number r the radius as well. And the correspondence there will be that r will be the length of the segment. With that in mind, the chord of a circle, omega, is a segment PQ such that P and Q are distinct points of the circle. A diameter of a circle is a chord that contains the center of the circle. And data will use the notation that if we're discussing a circle centered at O with radius r, we'll write that by putting a omega followed by the point O and the radius r. The interior of a circle omega is the set of all points such that the distance from the center is less than r, and the exterior is the set of all points where the distance to the center is greater than r. Continuing with a couple other definitions, we will say that a central angle of omega is an angle whose rays emanate from the center of omega. So in this drawing, we would say the angle AOC is a central angle because the vertex of that angle is the center of the circle. An inscribed angle of omega is an angle ABC such that the AB and BC are chords of omega. So in this particular picture, you'll see that AB and BC are chords of the circle. We would say that the angle ABC is an inscribed angle of the circle. Now, as we begin to prove things about circles, there will be an approach that is very common, very useful. We'll illustrate that approach with this proposition. So the proposition states that if AB is a diameter of a circle, as it is in this figure, the circle omega has center O, and C is a point on omega distinct from A or B, then the measure of angle AOC is equal to 2 times the degree measure of angle ABC. So in other words, the measure of this central angle is 2 times the measure of the inscribed angle. Now as we prove that, the thing to keep in mind is that this is, and we'll call P the point of tangency. Now in the videos that follow, we'll prove 3 statements about tangent lines and about angles within circles. You have a homework assignment due next time. It's a continuation of the homework assignment on last time's material. If you have any questions on the homework, please see data's text and send me an email if you'd like. See you next time.